In this video, we're going to just spend a little bit more time talking about parametric solutions. In a previous video, we introduced the concept and explained how parametric solution sets allow us to describe the solution set to a linear equation that has infinitely many solutions, right? So we just want to do a few more examples and say a little bit more about these parametric solutions. So for instance, in fact, let's just go through a couple examples to illustrate some key ideas. So let's say we have this linear equation, right? X plus y equals 4. And again, we have, there are infinitely many solutions to this. Now, when the linear equation has just a few variables, say 2 or 3, there are geometric ways that you can interpret this. So what I'm going to do is just do a little bit of geometry, right? And let's say we were to sketch this. Think of this equation as the equation of a line. There are only 2 variables, so we'll need a 2-dimensional plot to represent this. We have our x and our y. And if you were to use the intercept method back in algebra, you could easily recognize that here we have 2 solutions, 0, 4, and 4, 0. And if I write them as ordered pairs like this, then I can interpret this as the y-intercept, and then I can interpret this as the x-intercept. So if I plot these 2 points, let's just say 4 there, 4 there, and then connect them with that straight line, then that line has equation x plus y equals 4, or if you prefer to write it in your y equals mx plus b, it'll be y equals negative x plus 4, right? And that negative 1 coefficient tells us that our line has negative slope, and there it is. So geometrically, every point on this line would be a solution. So all these ordered pairs, including the 2 that I have listed here, these are just 2 really easy ones that you can identify by, again, using the intercept method. But all these points on the line, these ordered pairs, they satisfy this equation, right? So if I wanted you to give me a geometric description of all the solutions to this linear equation, you could just say, hey, here's a picture, and all the solutions are points on this line, right? But algebraically, what we want to be able to do is to describe all these ordered pairs, not with a graph, but with algebra. And that's where the parametric solutions come in. So for example, let's say I assign any real value to t. So if I'm sorry, to x. So if I say let x equals t, any real number, right? And that kind of makes sense because, when you think of the x value here, all the x values for points on this line, they could be any real number. But once I assign a parameter to the variable x, then I have to figure out what is the value of y that would satisfy the entire equation. So if I do this, then essentially what I have is this. And then solving for y tells me that whatever I pick for x, y would have to be 4 minus t, right? So again, over here, I've listed just 2 special ordered pairs. I could have found a couple more, but over here, just using this algebra, here is my solution set. So my solution set consists of all ordered pairs. One way is to describe it where I can put any real number there, and then whatever real number I have as my first in the ordered pair, then I have to do 4 minus that real number to get the y, right? And again, what would happen is if I plug, I could verify that every ordered pair of this form satisfies the original equation, right? And again, I've already stated up here that t can be any real number. I don't need to restate it again, right? But that's what it looks like if I were to choose x as my parameter. But what if I were to choose y? Right? There are two variables here, because if you think about it, I could easily rewrite this equation like this. It will be, exactly the same. I just have the y as my leading variable. And does it even mean that I have to use the leading variable as my parameter? Later on, you'll see that it doesn't really matter. But just to show you that you can have different parametric solution sets, I could do this. So here's an alternative. So, or I could say let y. Now, I could reuse t, right? But just to indicate that, or to give you an idea of the types of letters that we tend to use for parameters, t is one, s is another, r is another. So let y be equal to s, which is now going to be my free variable, right? So then I would have to figure out, let's say I were to pick the value for y, what would the x value be that would correspond to this? Well, I want that x value to satisfy this equation, right? Either one, it doesn't matter, right? So I could have x, so therefore x plus s is equal to 4. And then I can solve this for x, and x would have to be 4 minus s. And that leads to this solution set. Right now, in the first value in my ordered pair, or in this case expression, will be 4 minus s, and then the y value would be s, right? So these two, right, ordered pairs, they look different. One, because I'm using different letters for the parameter, but if you notice where the 4 minus the parameter is located in different positions, in the second position here as opposed to the first position here. But these are both correct definitions for the parametric solution set of this equation, right? So I'll just make a little note on this side. Parametric solution sets are not unique, right? So parametric solution sets are not unique. You can have different solution sets, right, for a single linear equation, right? Okay, so let's look at another example. And this second example, let's kind of up the number of variables. So far we've been using just x and y, but in our definition for a linear equation, we can have, it says any number of variables. So let's go from 2 to 3. And let me use subscripts now. So x1 plus 2x2 minus x3. Let's say that's equal to 10. All right. So this is our equation. And if you kind of look at this, you can see that you should recognize that this equation has infinitely many solutions. For example, I'm going to write down 3 very simple solutions, which should be obvious, right? So in fact, let me do this in a different color. If I let x1, before I do this. Let me go back here. So if I let x1 equals 10, and then I just let the other two variables equal to 0, then you can see that this is a solution, right? Because I've assigned values, right, to the variables, and these values satisfy the equation, right? But there is no rule that I have to make x1 equal to 10. What I could do, I could make x2 equal to 5, and then this product here in the middle term would equal to 10, and then I just have to assign 0 to the other two values. So I could do this. So this, and then that's 5, and then x3 again is also 0, is another solution, right? And then to get that third easy solution that I promised, I am going to assign x1 a value of 0, x2 a value of 0, and then I'm going to make x3 negative 10. Because if I put a negative 10 in this position, then that negative sign makes it a positive 10, and then 0's here means that the left-hand side simplifies to 10. So that's also a solution, right? How do we, what's the analogy here? Like, so we used ordered pairs in our first example. Well, if you have 3 variables, then you use what are called ordered triples, right? Because there are 3 variables now. So for this one, the convention is first, second, third, right? So 10, comma 0, comma 0 would be the ordered triple that corresponds to this solution. And then 0, 5, 0 would be the ordered triple that corresponds to the second solution. And then the third would be 0, 0, negative 10, right? But again, you can see we could continue this pattern. We could use less obvious values instead of 0, right? Which makes things simplified quite a bit in a linear sense. We could use different values, right? So how do we, just like up here, where we can use this parametric solution set, or this parametric solution set, we want to do something similar here. Well, let's think through the process for a second. If I gave you the choice, right? If I gave you the freedom, let me use the word freedom because we're going to use it in a more precise way in a second. If I give you the freedom to choose any value for, let's say, x2, any value for x3, you couldn't then just pick any value for x1. You'd have to figure out what the value of x1 would have to be so as to satisfy the complete equation. So after choosing 2 of the variables, I would then have to determine the third. I can't pick all 3 just at random, right? I could pick 2 at random, and then I would have to fully determine what the third variable is using algebra. So if you think through that process, it almost seems like now you have 2 free variables. And that's essentially true. So what I'm going to say is, and I'll show you, just like in the first example, that there are multiple parametric representations. There are multiple ones here. So the first one I'm going to show you is when I choose my x2 and x3 as free variables. So using, in fact, let me go back here now. So let's say using x2 and x3 as free variables. What would the solution set look like? Well, I'm going to use t and s. Now, the nice thing is x2 and x3 are like they're independent of each other. You can pick anything for x2 and then anything for x3, but then once you make those two choices, you'll have to figure out what the x1 value would have to be. So what I can do is I can say let x2 be any real number, let x3 be any real number, but not necessarily the same. So I'm not going to use t and t here, right? Because I don't have to choose the same value for x2 and x3. They could be the same as in the first example, right? But they're not the same here, right? And they're not the same here. So they don't have to be the same. So this is where using multiple parameters is useful. But once I do this, I have to figure out what x1 would have to be in terms of t and s. So therefore, x1 plus 2t minus s would have to be equal to 10. In other words, whatever number I put here and then multiply it by 2, and then whatever number I have here and subtract it from that result, when I add all of that to x1, I have to get 10, otherwise I don't have a solution. So what does this mean? Well, it's easy to isolate x1. So x1 will be negative 2t plus s plus 10, right? So if I choose t for x2 and s for x3, then x1 has to be negative 2t plus s plus 10. That leads me to this order triple. So put this expression in the first position, negative 2t plus s plus 10, and t in the second position, and then s in the third position. And this is my parametric solution set. So every ordered triple where I can put any number here, and then based on those two numbers, I use this formula to figure out what the first value in my ordered triple would have to be, would satisfy the original equation. And you can verify, right? You can verify that if you assign, for instance, t equals 0 and s equals 0, using this formula will give you the 10. If I assign a value t equals 5 and s equals 0, using that formula with these two numbers will give me the 0 that I observed earlier, and similarly for the third one. But then I can generate a lot more by picking anything for t, anything for s, and using this, which comes from the equation, right, to figure out what the complete order triple has to be, right? But there is no rule, right, at this point to say, well, I have to use x2 and x3 as my free variables. What if I use, so let's use a different pair. So let's use x1 and x2. Let's say using x1 and x2 as free variables. So this would be an alternative solution. You wouldn't have to do both, right? But we're going to come up with an alternative way of describing all the ordered triples that satisfy this equation. So I would let x1 equals t, and then x2 equals s, and therefore then I can use my algebra. So therefore t plus 2s minus x3 is equal to 10. And then you can go through and solve this pretty easily. What I'll do is I'll just add x3 and then subtract 10, and then I'll get this solution for x3. So x3 is t plus 2s minus 10, and that will give me my third variable. And in this case, the order triple would look like this. T S T plus 2S minus 10. Now what happens is, so again, how does this correspond with what we did earlier in green? Well, now if I assign T a value of 10 and S a value of 0, if I plug T equals 10 and S equals 0 into the third this formula here, it does give me a value of 0. Similarly, if I now assign T a value of 0, S a value of 5, doing that algebra gives me a value of 0, right? And just to show you that we can use lots of different combinations here. Let's do x2 or x1 and x3. So using x1 and x3 as free variables, what does that look like? Well, so let's use our same pattern. So we're gonna say let x1 equals t, x3 equals s, right? And then, so now let's solve for x2. So we have t and then plus 2x2 minus s is equal to 10. Solving this for x2, I am going to subtract t, add s, and then there's my plus 10, but now I have to divide by 2. Right? So in fact, I could do something like this. Let me write these as 3, separate fractions. So negative 1/2 t, and then plus 1/2 s, and then plus 5. So now, yes, you could even have fractions in your parametric form. There's absolutely nothing wrong with that. As long as you do your algebra correctly here, you're going to come up with a consistent solution set. So t in the first position, and now in the second position, I have to put this expression, the negative 1/2 t plus 1/2 s plus 5, and then in the third position I have to put my other free variable s. And this order triple again is consistent with the other 3. There are 3 different forms, right? And I'm going to say something a little it might not seem obvious right away, but it turns out when you're, in fact, let me state this. I'll just make this as another note, or kind of as a proposition. When a linear equation has infinitely many solutions, it has infinitely many ways, right, to represent those solutions parametrically, right? So to represent the solutions parametrically. So what that means is every, I forgot an A there, every linear equation that has infinitely many solutions can be it has infinitely many ways that you can pick your t and s, and it's not just t and s, there are other ways you can do it. So there are just many ways that you can describe the solution set. One more thing, the number of free variables or parameters. All right, so the number of free variables or parameters is called the degree of freedom. So the degree of freedom, right? And it tells you how many variables can you choose freely, right? And then whatever variables are left over, those have to be solved for in such a way that this equation is satisfied, right? So going back to, let me just kind of go back up here. So just kind of looking at this equation has 2 degrees of freedom, right? That was our number 2. And our number 1, there was only one free variable, so this one has 1 degree of freedom, right? And sometimes we just, in this context, we abbreviate degrees of freedom as DF, right? So I hope with these examples you're now getting a better sense of what these parametric solution sets represent and how useful they really are in describing the solutions of a linear equation when that equation has infinitely many. And hopefully you're looking forward to using this process in the future. I know I am.